Hi y'all, I'm Alex Trostle, and this is most high throughput expression data sets are underpowered. I did this work with my excellent co-authors at Baylor College of Medicine. In 2022, sequencing is as cheap as it's ever been, and it will only get cheaper from here. Researchers should really be doing more than the old gold standard of N of 3 per condition. We all know biological tissue can be highly variable. Obviously, it depends on the context, some more than others, but if you don't sequence enough samples, you will have false positives and false negatives in your results. It's always challenging to separate technical noise from true variance, and even though we'll never get rid of all noise, technical noise, we can increase statistical power to improve signal-to-noise ratio. To really show that 3 is not enough, and to get a sense of what is a better number for recommending replicates, we take a look at 3 different large and real-world data sets. We'll get to those in a second, but just for now on the left, further down, I have a power example. Just formally, power is the likelihood that a study will detect an effect when there is an effect. And then some challenges we had through this work are that effect size basically is per gene, right? So in an experiment like this, you have thousands of effect sizes. So theoretical power analysis is pretty difficult to apply. And seeing as each data set has a unique set of these distributions, we can't really build a parametric model that would cover everyone or even be generalizable really in a fair way. So we take an empirical approach. We use that to create a generalized recommendation. So then, up on the top right, we've got figure 1. This is those 3 data sets with high N. We've got human bulk transcriptome, nuclear mouse transcriptome, and fly proteome. In order to kind of simulate lower powered data sets, we wanted as many samples as possible. So if you've gone and done N of 10, for example, for the mouse nuclear, we can then simulate, well, what if you chose a 9, what if you chose an 8, so on and so forth. So this downsampling in the first row, you see that lower N numbers both yield fewer DEGs and have higher variance. So it's the variance, you see it better when it flattens out. We cut for a really high fold change in the second half of the panel. For row 2, we've got the power curves. So there's a continuous relationship between power and effect size. You've lost power with each of your sample. Actually, the lower N is further right, and that's because you basically are not detecting any DEGs whatsoever at really low fold change in those underpowered experiments. A natural kind of follow-up question to that as well, are we just getting the most important genes in the low? Sure, you have less DEGs, okay, I believe you, but what if the DEGs we're getting are just the important ones? Isn't that still useful? And into that, we've got row 3, which is effect size density curves. You have many low power colored distributions, and those are compared to the ground truth in black, that's either 8, 9, or 10. And you can see that the distribution is not like just basically shifted, right? It's not filling out the right side. Even in that top effect size density, when you basically get luckiest, it's still, right, basically a subset of the ground truth. Then to take a look at reproducibility in these low-powered experiments, we've got row 4. That is a simulation of, right, so you take a high N number experiment, you take N of 9, and you split that in half with non-overlapping samples. So basically you're simulating what if I had done this low-powered experiment, and then identically across the world, someone else had done the same one. We've done the same experiment. These mice are, these model organisms are biologically the same. How much noise is there? How much overlap are these 2 results going to have? And you can see that at best we've really got a third, even a quarter of genes are recovered as overlap. So these low power experiments are really not reproducible. Moving to figure 2 in the bottom left, we take that empirical approach that I talked about earlier. This is the density of power saturation. We pull 450 expression data sets from Recount, and in order to kind of make a diminishing return argument, we're not saying that 6 is the most DEGs. Obviously, the more samples, the higher N number you can have, budget and time permitting, the better. But in terms of when you get like an inflection point in number of degs, maybe that's a reasonable bang for your buck. So we're recommending 6 as a reasonable alternative to 3. Then moving right, we have an interactive web app that we developed. So you can either downsample your data and put those downsamples up to kind of compare the power and effect size. You can see those with ratio scale or absolute scale, absolute G number. Or the other way to do it, as in the example there, that's a bunch of low n number experiments. So you can see the kind of variance that you're dealing with at n of 3. You're doing the same experiment, or you have similar experiments, and looking at the power and effect size. But yeah, you can downsample your data. Our tool is up on GitHub there, and our preprints up on bioRxiv. As a set of conclusions there on the right, we would strongly recommend at least 6 replicates per condition if you want to understand differential expression. The quantitative advantages of just these few extra samples are very clear. Bad data holds science back, wastes valuable funding, and causes reproducibility issues. And with that, yeah, I'd like to thank Dr. Haryal in Chile and Saisudar Palsavetti, and thank you for listening.